Welcome to this presentation on design patterns in Go. In this session, we will explore the essential concepts of mastering composition, interfaces, and the foundational Gang of Four patterns within the context of the Go programming language. This guide is specifically designed for developers coming from a traditional object-oriented background who are looking to transition their skills into the Go ecosystem. We will examine how Go's unique approach to software architecture allows us to build robust and maintainable systems by rethinking classic design principles. Thank you for joining us as we begin this deep dive into modern Go development. The core shift we are examining is the transition from inheritance to composition. On the left, we see what is described as the old way, which relies on deep class hierarchies and is-a relationships. While common in many traditional object-oriented languages, this approach often leads to rigid, complex architectures, where a single change can ripple through an entire tree of derived classes, making the system difficult to maintain. In contrast, the Go way focuses on composition, or has-a relationships. Instead of building rigid hierarchies, we build structures by combining smaller, reusable components that represent specific capabilities. As shown in the diagram, struct A and struct B can both utilize component X while maintaining their own unique capabilities through components Y and Z. The fundamental lesson here is to stop thinking in terms of parent and child relationships and start thinking about capabilities. In Go, because you cannot create a child class that inherits fields from a parent, you are required to compose your types. This design choice encourages the creation of more modular, flexible, and maintainable software. To understand why Go stands apart in the landscape of modern programming languages, we must examine its approach to object-oriented design, specifically how it prioritizes composition over inheritance. Traditional object-oriented languages rely heavily on inheritance, which establishes is-a relationships, for instance, defining that a cat is an animal. This model results in compile-time binding, which is inherently rigid, and often leads to high complexity due to deep interlocking class hierarchies. Go, conversely, favors composition. This is built on has-a relationships, such as a cat having 4 legs. Because this binding occurs at runtime, it offers significantly more flexibility. This approach keeps complexity low by maintaining flat structures rather than convoluted trees. The core philosophy of the language is summarized by the idea that complexity is managed by shrinking the surface area. By avoiding the overhead of complex inheritance chains, Go allows developers to build systems that are simpler to reason about, easier to maintain, and more efficient to scale. Struct embedding is our first tool, representing a form of internal composition that establishes a flat surface for behavior. By embedding the engine type directly within the car struct, we enable a feature known as method promotion. As illustrated here, any methods belonging to the engine, such as a start function, become accessible directly on the car instance, streamlining the interface and enhancing code clarity. Our second tool focuses on implicit interfaces, which enable external composition without the need for an implements keyword. In this example, we define a speaker interface that requires a speak method. We then create a robot struct and assign it that exact method. Notice that we never explicitly state that robot implements speaker. This concept is known as duck typing. If a type possesses the required methods, it satisfies the interface automatically. This allows diverse types, like a robot and a duck, to be treated as speakers without any direct coupling, making our code more modular and flexible. Interface segregation is a fundamental design principle that champions the use of small, single-purpose interfaces over large, monolithic ones. This concept is visualized here through the analogy of building blocks. We have a reader and a writer. By keeping these interfaces segregated, we allow components to depend only on the specific behaviors they require. When a more complex interaction is necessary, we can seamlessly compose these small behaviors into a combined interface, such as a read writer. This pattern is a hallmark of the Go standard library, which utilizes io.reader and io.writer as primitive building blocks. By prioritizing small interfaces and composing them only as needed, we build systems that are more flexible, easier to test, and significantly more maintainable. Design patterns serve as the architectural foundation for scalable and maintainable software. While the original Gang of Four concepts were established decades ago, the unique paradigms of the Go programming language, such as its approach to interfaces and composition, require us to rethink how these patterns are implemented. In this session, we will examine 5 essential patterns reimagined specifically for the Go developer, bridging the gap between classic theory and modern idiomatic practice. The strategy pattern is a behavioral design pattern that enables the definition of a family of algorithms, encapsulating each one and making them interchangeable at runtime. This allows the algorithm to vary independently from the clients that use it. In this example, the shopping cart struct acts as the context, holding a reference to a payment strategy interface rather than a specific implementation. We then have concrete implementations, such as credit card and PayPal, which fulfill the interface requirements. As shown in the diagram, the shopping cart can seamlessly switch between these different payment methods. This structure provides significant flexibility, allowing us to add new payment strategies in the future without needing to modify the core shopping cart logic. Strategy, the rationale. This pattern serves as the ultimate weapon against the massive if-else statements that often overcomplicate code-based logic. By implementing the strategy pattern, we can adhere to the open-closed principle, allowing us to add new strategies, such as Apple Pay or crypto, without ever needing to modify the core shopping cart struct. Furthermore, it significantly improves testability by allowing us to test individual strategies in complete isolation. Ultimately, this approach ensures a clean separation of concerns. The cart doesn't care how the payment happens, only that it happens. The observer pattern is a behavioral design pattern that facilitates a one-to-many state notification system. This pattern is essential when you have a single object, often called the subject or publisher, that needs to automatically notify several other objects, known as observers or subscribers, whenever its state changes. Looking at our implementation in Go, we define a news agency struct. This struct maintains a slice of observer interfaces. By using an interface rather than a concrete type, the news agency remains decoupled. It doesn't need to know the specific details of its observers, only that they implement an update method. The notify all method demonstrates the core logic of the pattern. When an update occurs, the method iterates through the entire slice of registered observers and calls the update method on each one, passing along the relevant news data. The illustration on the right visualizes this dynamic perfectly. The central agency tower acts as our subject, broadcasting signals. Multiple observer dishes are tuned in to receive these broadcasts simultaneously. This architecture allows us to add or remove observers at runtime without modifying the news agency's code, promoting a highly flexible and maintainable design. The observer pattern represents the fundamental rationale and backbone of event-driven architecture. In this configuration, we have a data source that serves as the subject and a UI display acting as the observer. By introducing an observer interface between them, we create a system where the display can automatically update whenever the data source changes. This approach is used extensively in modern UI frameworks, as it allows components to react to state changes without being tightly bound to the source. This coupling ensures that our architecture remains flexible, maintainable, and responsive to real-time data updates. The factory method is a creational design pattern that focuses on delegating the responsibility of object instantiation. Its primary objective is to hide the complexities of concrete types from the client, allowing for a more modular and decoupled architecture. Looking at the code example provided, we see a function called getDatabase that accepts a string identifier. Depending on this input, it returns a pointer to either a Postgres or Mongo database implementation. Both of these implementations satisfy a common database interface. This process is effectively illustrated by the black box machine on the right. The client simply provides a parameter, such as the string Postgres, into the funnel, and the factory method handles the internal logic of creating the specific object. The final output is an object that implements the database interface, ensuring the caller remains unaware of the underlying concrete implementation details. The factory pattern serves the critical purpose of decoupling the caller from the implementation. This provides 2 main advantages. First, it offers abstraction. The calling code never needs to see a specific implementation, like a PostgreSDB struct. It only interacts with the database interface. Second, it simplifies configuration, enabling the system to decide which database to instantiate at runtime based on external configuration files. Ultimately, centralizing object creation in this way makes the entire codebase more modular and significantly easier to maintain. The adapter pattern is a structural design pattern that allows incompatible interfaces to work together through wrapping. Its primary purpose is to provide a bridge between two existing interfaces that cannot otherwise communicate directly. As shown in the code snippet, we have a legacy adapter struct that wraps a pointer to a legacy system. While our modern interface requires a process payment method accepting a float $64 value, the legacy system only provides a method for processing payments and cents. The adapter bridges this gap by performing the necessary unit conversion within its process payment implementation, multiplying the dollars by 100, and then calling the legacy system's underlying method. This is visually represented in the diagram, where the adapter serves as the intermediary component that translates requests from the modern interface into a format the legacy system can understand and process. The adapter pattern serves as a critical translation layer for survival in a modern software ecosystem. On the left, we have our core application, which contains the primary business logic we want to keep stable and clean. On the right, we often interact with external dependencies, such as the third-party billing API shown here, which can be unpredictable and complex. When an external API signature changes or a legacy system is updated, it often creates significant friction. Without an abstraction, these changes would force us to refactor large portions of our core codebase. By placing an adapter in the middle, we decouple our application from these external volatilities. The adapter handles the messy work of translating our internal commands into the specific format required by the third party. The primary advantage is maintenance efficiency. When the external provider changes their requirements, we only have to update the logic within the adapter itself. This allows us to follow a vital architectural principle. Don't rewrite the legacy system. Wrap it. By doing so, we protect our core application and ensure long-term system resilience. The decorator pattern is a structural design pattern focused on dynamically adding behavior to an object through wrapping. Looking at the code implementation in Go, we define a caching decorator struct that contains a core service of type data service. The fetch data method demonstrates how the decorator intercepts the call. It provides a hook to add caching logic before delegating the final request to the wrapped service. This relationship is visually represented by the nesting dolls on the right. The caching decorator serves as the outer shell, adding additional functionality, in this case caching, without altering the underlying data service, effectively extending its capabilities at runtime. Functional decorators, often referred to as middleware, offer a powerful way to compose behaviors by wrapping functions. In this example, we are building a processing pipeline by nesting function calls. We start with the core operation, save user, and wrap it with timing to measure performance. That result is then wrapped with logging to provide visibility into the process. This approach allows us to keep the internal logic flat and modular, effectively avoiding the complexities of deep struct nesting while maintaining a clean, extensible codebase. Let's explore an advanced approach to mocking using composition. By applying dependency injection, we significantly improve the testability of our code. In the production example at the top, our user service is initialized with a concrete S3 store. This implementation interacts directly with live cloud infrastructure. For testing purposes, however, we want to isolate our service from these external dependencies. Because our service uses composition, we can easily inject a mock repo instead of the S3 store. This allows us to simulate various scenarios and edge cases in a controlled environment without ever touching the actual cloud. This pattern decouples our components, making our codebase more flexible and our tests much faster and more reliable. Interface segregation is a powerful principle that allows for more precise requirements through granular behaviors. In this example, we have a comprehensive storage system that includes functions for reading, writing, deleting, and auditing. Rather than forcing a consumer to depend on this entire monolithic structure, we can break those capabilities down into smaller, focused interfaces like reader and writer. Observe the display data function. By specifying that it only requires a reader interface, we decouple it from the full storage implementation. This abstraction ensures that the function only knows about the specific behavior it needs to perform its job. This approach provides significant extensibility. For example, if you implement a read-only store in the future, it will work immediately with the existing display data function, without requiring any code changes. This demonstrates how fine-grained interfaces lead to more modular and maintainable systems. The Go pattern checklist summarizes key architectural strategies for writing idiomatic and efficient code. First, we have struct embedding, which is ideal for internal composition when you need to share data and fields across different structures. Next, we emphasize the use of small interfaces. These are essential for defining specific behaviors through external composition, promoting a highly modular design. When dealing with external dependencies, we use adapters to wrap legacy code or third-party APIs, maintaining a consistent interface within our own codebase. For managing dynamic behavior and implementing middleware, we rely on functional options and decorators. Ultimately, these patterns align with our guiding principle that simplicity is the ultimate sophistication. Complexity is often mistaken for sophistication, but in system design, simplicity is the ultimate goal. When we break down multifaceted problems into modular, manageable components, we create architectures that are resilient, maintainable, and scalable. These visual representations remind us that whether we are designing logistics, hardware, or software, the most effective solutions are built on clear, fundamental blocks. By stripping away unnecessary layers and focusing on core functionality, we ensure our systems can evolve alongside our needs. It is time to move beyond the convoluted. Go build simple systems.